Welcome to ilectureonline, and in this next set of examples we're going to show you how to find the volume that is created by taking an area defined by a set of equations and rotating it about some sort of axis. The best way to show you that is simply by showing you some examples. We can go through the theory, but that doesn't really mean much to most people. Let's just go ahead and show you several examples so we can catch on how to do that. That's really what it comes down to, is a good technique on how to do that. So here we have an area that's bounded by the equation y equals x squared, which is a parabola. We did not draw this part of the parabola because we're also bounded by the line y equals 5, which is this line right here, and the line x equals 0, which is the y-axis. So it's this area right here, and we're going to rotate that area about the y-axis. So when we rotate it like that, we get kind of like a bowl-shaped object. So we're going to rotate that all the way around, and so we end up with something that looks like this. But it's complete volume-wise, so it's rotated around like that, so we kind of like a bowl coming up flat at the top and parabolic in shape all the way around like that. Okay, so that's what we're trying to find the volume of. How do we do that? Well, we need to get a volume element. We need to find a dV. And there's different ways of doing that. We can get what we call flat disks, we get washers, we get hollow cylinders, all kinds of ways in which we can do that. In this case, since it's a solid object all the way around, we can maybe just take a slice like this. So we can take a small little slice. So the thickness of the slice is a dy. So the thickness of the slice is a dy. And then the area of the slice is simply the area of a circular object, right? This would be like a disk, a circular object at the top. And so the area would be equal to pi r squared. So what I'm going to do is I'm going to take this and redraw that small little volume element. And when I do that, it would look kind of like this. There's my volume element. It would be a small little disc shape. So if I take a saw, if this is a solid object, and I take a saw and I cut it like this, cut it like that, take this small little sliver and put it over there, I would get like a small thin disc where the thickness of the disc is dy, and this would be the radius of the disc, r. And so therefore the volume right there, the small little volume of this small little disc called dV would be equal to the area times the height, which is dy, and the area would be pi r squared times dy. The question now in this case is, what is the r equal to in terms of what I have drawn here? And notice the r is simply this distance from there to there, so this would be the r, and that would be the distance from the x-axis to the outside of this curve right here, which is defined by y equals x squared. And so r then in this case would be equal to distance from 0 to what x is defined of by this right here, so it would be this x, call it this x sub 1. So this distance right here would be simply equal to x. All right, so then when I do that, if I plug that in here, I can say then my volume element is equal to pi times x squared dy. Okay, so does everybody see here that this is x equal to r? X is simply distance from 0 to the outside here of this volume element, or I shouldn't say a volume element, but this shape right here, and the distance from there to there is simply defined by this equation right there. So I'm dealing with this x right there. Since I call it x sub 1, let's call it x sub 1 here, and let's call it x sub 1 there, so we don't lose track of which x we're dealing with. Okay, now what do I do when I want to find the whole volume? Well, I'm going to go ahead and take the next slice, the next slice, the next slice, the next slice, and add them all up. All these little slices are all dVs, and they all have the same dimensions. It's pi r squared times the height dy, and r will always be equal to x no matter where I'm at. So there's always a value equal to x, which is the outside minus the inside. The outside is this x right there. The inside would be x equals 0. So I want to find the whole volume. The whole volume is equal to the sum of all the little dVs, and the sum, of course, is the integral of all the dVs. I'm going to integrate from y equals 0 to y equals 5 because I'm given the upper limit here and the lower limits, so from 0 to 5, and these are y limits. And dV is defined right there, so this is equal to the integral from y equals 0 to y equals 5. Instead of dV, I can write pi x1 squared dy. Now you can see that my limits are in terms of y, my differential is in terms of y, but my variable is in terms of x. So I'm going to have to replace that x by what's equal to in terms of y. So when I come up here, I see that x1 squared is equal to y. So instead of writing x1 squared, I'm going to write y. So this is equal to the integral from y equals 0 to y equals 5. And notice that pi is just a constant, so I can take that outside integral sign. So I'll write it here, pi. And instead of x1 squared, I'm going to write y dy. And now I'm ready to integrate, because that's an easy integral. Y dy integrated becomes y squared. So this is pi y squared over 2. I add 1 to the exponent, divide by new exponent. And the limits are from 0 to 5. When I plug in the upper limit, I get this is equal to pi times 5 squared over 2. When I plug in the lower limit, of course, I get 0. And that means that this is equal to 25 over 2 pi as the volume of this thing created when I took this area right here, bounded by the parabola, the straight line y equals 5 and the y-axis. If I took this and swung all the way around the y-axis, getting this bowl-shaped region, I take a slice, which is my little dV volume. I then add it all up. I add up all the little dVs, give me the total volume, and that will then be 25 over 2 pi. And that's how we do a simple example like this. And I have a whole bunch of examples ready for you. So if you want to get the feel for it, you want to look at a number of different examples, because the technique will vary depending upon what the shape is that you end up with. And here's our next example of how to find the volume of something, where we take like an area defined by some equations right here. We have y equals the square root of x minus 2, and x equals 5. X equals 5 is this line right there. So let's see, that's 3, 4, 5. And here's the equation, y equals the square root of x minus 2. And if we then rotate that about the x-axis, we get something like this that would then have a volume to it. So it's kind of like a bowl shape or parabolic shape object facing this way, positive x direction. We're trying to find the volume of that. How do we do that? Well, in this case again, we're going to take a slice of that and call it a small little dV. So here's my slice, like that. And if I take that and look at it on the side, it kind of looks like this. Right, so there we go. And the thickness of the slice, the little width of the slice, that would be a small little dx. So that's my small little dx. That's the center of the slice. I have a radius like this. This would be my radius. So my radius would be this distance right there. That's my radius. And what would my radius be equal to? Well, starting from the x-axis up to this point right there, this would be the same as the height. I could call it a y. And the height would be defined by this function right there. So I'm going to call this y1, y1. And so that way I keep track of what I'm dealing with here. So the radius of this little disk called r is equal to the height defined, or the y defined by this function right here as a function of x. So for this particular value for x, it'll be this high right there. And so the small volume dV can be defined as the area of this disk, which is pi r squared, times the thickness, which is dx. And of course, since r is equal to y1, that would be equal to pi times y1 squared dx. And then coming up here, if y1 is equal to this, then y1 squared would be equal to this square, which would be x minus 2. With other words, I can replace y1 squared by x minus 2, and my small little volume element, dV, is equal to pi times x minus 2 times dx. And if I then integrate that, sum up all the little slices, which is integrating it from this limit to that limit, from x equals 2 to x equals 5, I can find the volume of that. So my volume is going to be equal to the integral from 0 to, not from 0, because I said 0, actually I meant 2. 0 is over here. This is 2, so from 2 to 5 of all my dVs. And so that would be the integral from 2 to 5, and dV is equal to pi times x minus 2 times dx. And of course, since pi is a constant, I can move that outside integral sign. So this is equal to pi times the integral from 2 to 5 of x minus 2 dx. And I'm ready to integrate. That's an easy integral, of course. So the integral of x would be x squared over 2. And I can't forget my pi. My pi is still there. So that's pi times x squared over 2 minus 2x. That would be the integral of x minus 2, and then the limits, of course, are from 2 to 5. So when I plug in my upper limits, I get pi times. Plug in the upper limit, I get 5 squared over 2, which is 25, or I might as well just do the substitution first, so you can see how that works. So 5 squared over 2 minus 2 times 5. So that's when I plug in the upper limit, and I subtract from that when I plug in the lower limit. So let me put some parentheses around that. So minus, when I plug in the lower limit, I put a 2 in there. That would be 2 squared over 2, and that would be minus 2 times 2. So this is what I get when I plug in the upper limit, and this is what I get when I plug in the lower limit. So now I need to simplify. So let me come over here. So we get pi times 25 divided by 2 minus 2 times 5, which is 10. And I have minus 4 over 2, which is 2, so minus 2. And a minus times a minus makes that a plus, plus 4. So this is equal to pi times, I get minus 10, minus 2 is minus 12, plus 4 is minus 8. So I get 25 over 2 minus 8. Of course, 25 over 2 is 12 and a half. So this is equal to pi times 12.5 minus 8, which is equal to 4.5 pi. And that would be the volume of that object created when we take this piece right here, which is defined by y equals the square root of x minus 2, and then at the end, x equals 5. Take this and rotate it around, and then take a slice of it. Here's my little slice. I find my dv in terms of y. Then I replace y by what y is equal to, which is square root of x minus 2, and then I go ahead and integrate. And that's how we do that. Here we're doing our next example of how to find the volume created by taking an area defined by two equations. So here we have a straight line, y equals x, a parabola, y equals x squared, and so they intersect in two places and they bound an area. If we take that area now and we rotate it about the x-axis, we end up with some sort of cone volume that has a varying thickness wall. So think of a cone sticking out where the wall is very thin at the edges and thick in the center, and I've kind of tried to draw that here. Not have very good drawing skills, but here we go. That's kind of what it looks like, and we're trying to find the volume of that. How do you do that? Well, the best thing to do is to find a small dv, a small little volume section of that. And the best way to draw that is to draw it vertically. And the reason is because that way the lengths are always differentiated between the straight line and the curve of the parabola. What I mean with that is if we draw a small little section like this, we take a small little slice. Remember, this is in 3D, three-dimensional. You end up with a washer. Let me try to draw the washer over here. It'll look like this. There we go, a little thickness to it, like so. Okay, so there's a little washer that we get by slicing this volume. And the thickness of that would be this right here. So it would be the thickness that is dx. And so the thickness of that would be a small little dx right there. And then the radius, so we have an inner radius, let's call that R1, and an outer radius, let's call that R2. Notice, how does that correspond to my drawing here? Well, from the center, which is right here, I have an inner radius, which goes to there, which is R1, and an outer radius, which goes to there, which is an R2. So now we have to determine what those inner and outer radiuses are in terms of x and y. So let's try to do that. We call this the dv, a small little volume, which is equal to the surface area of that disk or that washer times the thickness, which is dx. And so the area of this would be equal to pi times the outer radius squared, so that would be R2 squared minus pi times R1 squared, so that would be the area of the disk minus the area of the hole, and multiply that times dx, the thickness of it. That will give you the volume of this washer, and so that can be written as pi times R2 squared minus R1 squared times dx. So that's a small little volume. And you'll probably already guess what we're going to do. We're going to then integrate all those little washers all the way from here to there. So that's a summation. That's what we call an integration. But we can't use the variables r. We have to replace that with the variables in x and y. So the distance from there to there is simply distance from 0 to the curved line, which is this y right there. So let's call that y1. And so we can then say that r1 is equal to the distance from the x-axis to the parabola, which is defined as y1. So this can be written as pi times y1 squared. And then r2, oh, is that, no, oh, sorry, I'll take that back. I've got r2 there. So I was talking about r1, so that would be minus y1 squared dx. So I replaced r1 by y1, which is correct right here. So r1 would be the distance to the curved line, which is this function right here, which is y1. And r2 is a distance to the straight line, which is my function right here. Let's call that y2. Instead of writing r2, I can write y2. So y2 squared. So now I have defined my small little volume, my dv, in terms of y and dx. Of course, I still can't integrate it this way because y is, of course, a y value. Variable and x is an x variable. You can't integrate y's and x in the same integral. Unless, of course, you do a double integral, but that's not what we're doing here. So now we have to replace y1 and x1 by what they are in terms of the x variable. So y1 is x squared, and y2 is x. So this is equal to pi times y2 can be written as x, and that's then squared, minus y1. y1 is x squared, and of course that's squared as well, dx. So finally we can say that this is equal to pi times x squared minus x to the 4th power dx. And now we have our small dv, our small volume element, this little washer, expressed in terms of x, the x variable, and we're now able to integrate that so we can find the total volume. So the total volume v will be equal to the integral, which means the sum of all the little slices. If we slice it all up, all the way from x equals 0, all the way to x equals 1, we add them all up, we get the total volume of the structure right here. So volume is going to be integral of all the dv's, which is the integral from x equal, start at 0, to x equals, where they cross, which is at 1, and our dv is equal to pi. I can take the pi outside integral sign. I can put the pi in front because it's a constant, times the quantity x squared minus x to the 4th times dx. And now I'm ready to integrate. So when I integrate that, this is equal to, that would be x cubed over 3. Remember, you add 1 to the exponent, divide by the no exponent, minus x to the 5th over 5. The whole thing evaluated from x equals 0 to x equals 1, which is equal to, when we plug in the upper limit, we get 1 over 3, because, of course, 1 cubed is still 1, minus 1 over 5. And when then we subtract the lower limit, we plug in zeros, we simply get 0, so it would be minus 0 plus 0. There we go. And so finally, we then know it's 1/3 minus 1/5. We have to put that over the same common denominator. Ooh, and I can't forget my pi here. Let's see, let me move this out a little bit. Equals pi times, we can't forget the pi, that is still there, so we still need to put a pi in front there. There we go. Okay, and so now we sum these up together over the common denominator. So this is pi times over 15 would be the common denominator. And since 3 goes into 15 5 times, we write 5 over 15. And 5 goes into 15 3 times, so 3 times 1 is 3 over 15. So finally we can say that this is equal to 2 over 15 times pi. And that would be the volume of that strange little contraption by taking this area, which is bounded by those two equations, and we rotate it all about the x-axis to get the structure right here, and the volume of that structure would be equal to 215 pi. And the whole trick is to simply slice it up, take a little slice. Imagine that little slice will be a little disc that has a hole in it, so it's kind of like a washer, which has an inner radius and an outer radius. The inner radius is the distance from the x-axis to the equation y equals x squared. That would be the parabola. Let's call that y1. So instead of r1, we can write y1 like that. And the outer radius is r2, which is distance from the x-axis all the way to the straight line, which is y2 equals x. And now finally we replace the y1 and y2 by what they're equal to in terms of x, and then we integrate. And that's how we do that. And our next example is the same as we did previously, but instead of rotating the area bounded by the line y equals x and the curve y equals x squared, instead of rotating it about the x-axis, we're now going to be rotating it about the y-axis. So you get kind of a parabolic bowl with straight sides on the inside, but all the way around like that. It's kind of a strange looking bowl, but hey, it would work, I suppose. And we're trying to find the volume of that. So how do we do that? Well, in this case, we're going to slice it like this. Again, the reason why we slice it like that is because we end up with a washer. You'll see in just a moment why that is so. So if we slice it like this, not only do we end up with a washer, but the nice thing about it is that the inside of the washer will be bounded by the straight line, and the outside of the washer will be bounded by the parabolic curve on both sides of the washer. And so it's exactly what you want, all the way from the limiting point, the 0, 0, all the way to where the two lines meet over there, 1, 1, and negative 1 and 1. So that would work out the best. Let me draw what that washer would look like. So here's our washer on the outside here, like so. Then too good of a job, but at least I think you can see what it looks like. So that's the washer right here. If we slice it like this and we take it out, since it's a volume region like this, you can see that that's what it would look like. The inner radius right there from there to there, let's call that R1, and the outer radius, let's call that R2. And the thickness in this case would be dy, because it would be this thickness right there. So this thickness right there would be a small little dy. And R1 would be the distance from the y-axis to the inside of the washer, so that would be R1 right there. And then the outside radius, that would be R2, would be like that. Now you can see here that the inside radius would be from 0 to the x of the straight line. So that would be x1 right there. Let's call this your x1. And let me get rid of these subscripts on the y. We no longer need those. That's from the previous problem. So that will become our x1. That's the distance from the y-axis to the straight line, and it would be an x value, and so therefore we label that as x1. The distance from there to the outside radius, that would be the distance from the y-axis to the curved function here, the y equals x squared function, so that would be your x2 right there. Okay, so now what we can do is we can replace R1 and R2 by x1 and x2. Okay, so our volume then, our dV, which is equal to the surface area of this washer times the thickness dy, and the surface area would be equal to the area of the whole washer if there was no hole in it, so it would be pi times R2 squared minus the area of the hole, pi R1 squared, so that will give us the surface area of that washer, and then times the thickness will give us the volume dV. And of course, instead of using R and R2 and R1, we're going to use x2 and x1. So this is equal to pi. We can factor out a pi. That would be x2 squared minus x1 squared times dy. Now we're not quite done yet because we can't integrate x's and y's in the same integral. So we have to convert from the x1, x2, y1, and y2. So since x1 is equal to y, we could replace x1 by y. So this can be written as pi times y squared dy. And instead of x2 squared, we come over here, x2 squared is actually equal to y, so we can replace that simply by y. And now we're ready to integrate. Now we have our volume, our little volume element dV. And we can then say that the total volume will be equal to the integral of all the dV's, which is the integral of what dV is equal to. We'll take the pi outside integral sign. We have y minus y squared times dy. And the limits of integration, we're going to integrate from the bottom of the bowl, which is y equals 0, to the top of the bowl, where y is equal to 1. So from y equals 0 to y equals 1 are your limits. And now we're ready to integrate. So this is equal to pi times, and I guess we don't do it like that. We use brackets. So we go y squared over 2. So you add 1 to the exponent, divide by the new exponent, minus y cubed over 3. And the limits of integration from 0 to 1. So now we go ahead and plug in the upper limit. So this is equal to pi times, that would be 1/2 minus 1/3, because when you plug in the 1, you get 1 squared, that's still 1, and 1 cubed, that's still 1, minus when you plug in the lower limit, and of course when you plug in the lower limits you get 0, so you don't need to do that. And then you combine those by getting the same common denominator, which would be over 6. And since 2 goes into 6 3 times, this becomes 3. 3 goes into 6 2 times, that comes 2. And so therefore the volume would be 1/6 pi. And there you go. That would be the volume of this weird looking bowl. That's how we do that. And then here's our next example of how do we calculate the volume by taking an area and rotating it about an axis. Now you've seen this particular equation before. We have a parabola y equals x squared. We have a straight line y equals x. So they cordon off an area right here. But in this case, we're going to rotate the area about a different axis. It's going to be the axis y equals 5. So now we're taking this area right here and simply rotating it about like that all the way around. So we get this volume, and I'm trying to draw what this volume looks like. So you have this area right here rotating all the way around. So we have a bowl with a big hole at the bottom. Basically, that's how you want to look at it. And so what is the volume of that? Well, again, the way you want to do that is to draw or to slice off a little slice of this. And again, we're going to get a washer for this. So if we slice it like this, we end up with a washer that has a very big hole in it. So there it is. So you can see that the radius of the inner portion of the washer will be, let's call it R1, and the radius to the outside of the washer, let's call that R2. So you see that's the radius the inside, the outside. Let me draw the washer over here so you can see it. So the washer will look like this, like so. Okay, there you go. That's what this washer would look like. And then from the center to the inside radius, let's call that R1, and then of course to the outside radius, let's call that R2. And so the thickness of that washer, and let's see, the thickness would be a small little dx, so a little thickness would be dx, in such a way that the volume, dV, would be equal to the area of that washer times the thickness, which is dx, and the area would be equal to the area of the outside dimension. That would be pi times r2 squared minus pi times r1 squared. And of course, this pi times r1 squared would be the area of the hole. So the whole disk minus the hole gives you the area of the washer times the thickness dx, which gives you the volume of the washer. And then of course, we're going to sum up all the washers. When we slice this whole thing up in infinite number of slices, we add them all up. That's of course the integral of all the dVs. Now we can't use r's, so we have to convert from r's to x's and y's. So first of all, this distance from there to R1, the radius right here, from there to there, that is the limiting factor here is the straight line, y equals x. So that would be the distance from here, that would be 5, minus the distance here, which would be y. Remember, this here would be, let's call it y1. Call this y1. So this distance from the x-axis to the straight line is y1. The distance from the x-axis to there is 5. So I take 5 minus y1. That gives me the remainder, which is r1. So therefore, I can write this as, I can factor out a pi, and I'm left with something minus, instead of r1, we're going to write 5 minus y1. 5 minus y1, and that's squared times dx. So now replace r1 by 5 minus y1. We're going to do the same for R2. R2 is the distance from there to there. So we take this whole distance, which is 5, and subtract this distance from it, the small distance right here. And that would be, let's call it y2, because the distance from the x-axis to the parabola. So we call this y2. And so if you take 5 minus y2, we get the distance R2. So here we write 5 minus y2. Of course, we have to square it as well. So now we have to convert it from r's to y's, the variable y. Of course, we can't integrate y's and the x's, so now I have to convert from the y's to the x's. Now y1 would be x, and y2 would be x squared. So this is equal to pi times the quantity 5 minus y2 would be x squared, quantity squared, minus, that would be 5 minus y1, and y1 is x. We also have to square that times the x. And now we have a nice little volume element, that little washer there. And now all we have to do is integrate all those volumes, all those dVs. However, let's clean it up a little bit. Let's work out the squares here. That we multiply or square the binaries. So this is equal to pi times, that would be 25 minus 10x squared plus x to the fourth. So when I square this, I get this. Minus, I still need parentheses so I don't mess up with the minus sign here. So here we get 25 minus 10x plus x squared, the whole thing times dx. And then if we apply the negative sign in there, we get this is equal to pi times, we have 25 minus 10x squared plus x to the fourth minus 25 plus 10x minus x squared, the whole thing times dx. And I use the bracket, so I might as well put a bracket here as well. Okay, and then finally, let's see what things cancel out. Here we have 25 minus 25, so those cancel out. So I'm left with pi times, have an x to the fourth. I have a minus 10x squared minus x squared, that's minus 11x squared. And finally, so that's gone, that's gone, that's gone, and finally plus a 10x right there times dx. And this is my dv, and now I'm ready to integrate. Okay, let's come over here. We have a little bit more room. So v would be equal to the integral of all the little dv's, which is equal to the integral of, and I can take the pi outside integral sign, that would be x to the fourth minus 11x squared plus 10x all times dx. And what are my limits of integration? Well, I'm going to integrate from x equals 0 to x equals 1 from left to right. So x equals 0 to x equals 1. Now I'm ready to integrate, so that's fairly straightforward. This is equal to pi times x to the fifth over 5 minus 11x cubed over 3 plus 10x squared over 2, and the whole thing evaluated from 0 to 1. Now you notice that if I plug in the lower limits, I get 0, so I can ignore the lower limit. I just need to plug in the upper limit. So this is equal to pi times, when I plug in 1 here, I get 1/5. When I plug in a 1 here, I get 11/3, so that's minus 11/3. And if I plug in a 1 here, I get 10/2 plus 10 over 2. All right, for me to combine that, I need to find the lowest common denominator, which looks like it may be 30. All right, so this is equal to pi times, since 5 goes in 36 times, that would be 6 over 30, minus 3 goes into 30 10 times. 10 times 11 is 110 over 30, and that would be plus, since 2 goes in 30 15 times, 15 times 10 is 150. All right, so this is equal to pi times 150 minus 110, that's 40, plus 6 is 46 over 30. And finally, if we simplify that, it would be 23 over 15 times pi. And that should be the area, or not the area, but that should be the volume when we take this area that's defined by the straight line in the parabola. If we rotate that about the axis, y equals 5, we get this shape right here. We take the volume of that, should be 23 over 15 pi. That's how we do that. And now, next example on how to find the volume created by taking an area that's defined by the line y equals 4 and the parabola y equals x squared, and we're going to rotate this area about the axis x equals 5. Kind of rotate it around like this, and so you end up with a structure that looks like this. It's almost like a baking pan for cake if you think about it. We have the center right here and kind of like a curved, you could put a nice little lemon cake right in there. Sounds good. Anyway, we're trying to find the volume of that, and the question is, how do we do that? So in this case, the place where the cake would go, that is the volume we're trying to determine. So how do we do that? Well, we need to slice it up in small little dv somehow, and how do you do that? Well, the first inclination might be to try to slice it like this. And I'm going to use a different color for that, because ultimately that's not what we're going to end up doing, but I want to show you why. So if we were to slice it like this, and we're trying to develop a little washer, you can see how that would be a little washer if we did it like this. The problem is that the inner radius, going from there to there, would be defined by the equation y equals x squared, and the outer radius would also be defined by the equation y equals x squared. And that would make it difficult to work with, so that's probably not the right way to do it. What's probably a better way to do it is to go and build something like this. Slice it like this, and like this, in such a way that you end up with a hollow cylinder. Notice that this is rotated about the x equals 5 line right there, and notice that small little segment here would go all the way around and form like a cylindrical shaped object. And let me draw that cylindrical shaped object over here. It would kind of look like this. Ooh, I made it a little bit too thick, but I think you're getting the idea right there. So you end up with a small little thin shelled cylinder. And notice that if we do that, the radius from there to there, that would be the radius, we'll call that r, and let's call this the height of that cylinder, h. So you can see that from the center of the cylinder to the edge there, that would be r, and the height here, that would be h, and the thickness from there to there, well, since we're in the x direction here, this is the y-axis, and this is the x-axis, you can see that the thickness of that would be a small little dx. So we put a little dx right there. And now we're ready to define the volume of that little cylinder, thin shelled cylinder. That would be your dV. So how do we do that? Well, the idea to think about it is if you have like a hollow cylinder with a thin edge, if you were to cut it like this and lay it flat, we end up with a rectangular shape that has certain thickness. The thickness would be dx, and the rectangular shape would be, the length of it would be the circumference of this. So it would be 2 pi times the radius, that would be the circumference, times the height. That would be, if you cut it and lay it flat, that would be the area of the rectangle, and then times the thickness dx will now give us the volume of this little hollow cylinder. So now we have the volume of the little hollow cylinder. You can imagine then that you're then going to open up a little bit more and then more and more, and just draw more and more cylinders, so when they all are filled up together, they form the complete volume of this thing as it rotates completely around. That's what we're trying to do, which means that the volume will simply be equal to the integral of all the dV's. We'll sum them all up. Okay, now we have our volume in terms of, or our dV in terms of r and h, and the differential is dx, so we have to somehow convert our r to x and our h to x. So let's do it one step at a time. First of all, the radius r would be the distance from the y-axis to this line right here, which is 5, minus this distance right here. So this would be the x value from the y-axis to where this cylinder hits the parabola y equals x squared. So r can be converted to x. This value would be x by simply saying that r is 5 minus x. So therefore dV is equal to 2 pi. Instead of r, we can write 5 minus x, which is the distance from the center of the cylinder to the edge of the cylinder, and that would be this distance minus this distance, which means 5 minus x, which gives me r. All right, now the height. So the height will be going from there to there. Now the upper line here, the boundary, is the y equals 4 line. And what we want to say then is that this h is equal to the full distance from there to there, which is 4, minus this distance right here. And that would be the y value of the parabola, y equals x squared, when we get to that point. So it would be 4 minus y. And so we can replace h by 4 minus y times dx. Okay, now the only thing left to do is to convert y to x, and of course for that we need this equation right here. We realize that on the parabola y is equal to x squared, so instead of writing y we'll write x squared. So now we have our volume dV is equal to 2 pi times 5 minus x times 4 minus x squared times dx. And then the only thing left to do is just multiply all that out, so we get one nice expression, and then we can go ahead and integrate that. So dV is equal to 2 pi times 5 times 4, which is 20. 5 times minus x is minus 5x squared. Minus x times 4 is minus 4x. And minus x times minus x squared is plus x cubed times dx. And now let's rewrite it slightly better. We have dV is equal to 2 pi. And usually we like to write it in descending order. So we have x cubed minus 5x squared minus 4x plus 20 times dx. And now we have a nice expression for our small little dV, and all we have to do is plug that in here, find the proper limits of integration, and now we can go ahead and find the volume. So this would be equal to the integral, or I can take 2 pi outside the integral, so 2 pi times the integral of x cubed minus 5x squared minus 4x plus 20 times dx. And our limits of integration, let's see, we're integrating across dx, so we're going to go from x equal 0 to x equal, well, wherever these meet. Now, actually, we can do that because then we're forgetting this part of the integral, aren't we? We have to go all the way from there to there. We have to integrate across this entire width. So where do these two equations meet? All right, that means we have to solve these two simultaneously to figure that out. So let's do that. We'll do that next. So we have x squared is equal to 4. Therefore, x is equal to plus or minus 2. That means that the x values of these 2 points is 2 and minus 2. The y values, well, we plug in 2, we get 4 and 4. So that will work. There we go. So we actually have to integrate it from all the way from minus 2 to positive 2. X equals minus 2 to x equals plus 2. And now we're ready to go. Okay, so this is equal to 2 pi times, let's integrate this, so we have x to the 4th over 4 minus 5x cubed over 5, oh, nope, over 3. I'm looking at the wrong number here. Divided by the new exponent, 3, minus 4x squared over 2, and plus 20x, and the whole thing evaluated from minus 2 to 2. The inclination would be, well, let's see, can I not just go from 0 to 2 and then just double it? And the answer is no, you will not get the right answer. You have to plug in both the upper and the lower limit. The reason for that is the lower limit has a negative on it, and some of these are odd order, first order, third order, so you get a different result with the positive and the negative numbers, so you'll not get the same thing by going from 0 to 2 and doubling it. That will not work in this case. We simply have to go through the work of plugging the upper limit and then subtracting when we plug in the lower limit. So let's go ahead and do that. So this is equal to 2 pi times when we plug in the upper limit. 2 plugged in here, that would be 2 to the 4th power, which is 16, divided by 4, which is 4. 2 plugged in here, that's 8 times 5 is 40, divided by 3, which would be minus 40 over 3. Plug in the upper limit here, we get 2 squared, that's 4. 4 times 4 is 16, divided by 2 is 8. And finally plug in 2 here, plus 20 times 2 would be plus 40. Minus, when we plug in the lower limit. All right, now when we plug in the lower limit, minus 2, since this is an even exponent, we get the same result. That would be 16 divided by 4, which is 4. Plug in the lower limit over here, minus 2 cubed, that's a minus 8. Times 5 is a minus 40 divided by 3, but this minus makes it a plus, so that's plus 40 over 3. Plug in negative 2 over here, that would be a positive 4 times 16 divided by 2 is 8. With a minus, that's minus 8. And finally, a minus 2 in here, that gives me minus 2 times 20, minus 40, minus 40. Okay, so now we just have to combine that. Well, first what I would like to do is get rid of this negative sign and get rid of the parentheses so we can see what we can easily simplify. So this is equal to 2 pi times, we'll repeat, 4 minus 40 over 3 minus 8 plus 40. We get minus 4. Minus times that gives me minus 40 over 3. Minus times a minus gives me plus 8, and minus times a minus gives me plus 40. All right, so now we can simplify things a little bit because we have a 4 and a minus 4, that cancels out. We have a minus 8 and 8, that cancels out. So now all we have to do is add the 40. So this is 2 pi times 40 plus 40, which is 80. And minus 40 over 3, minus 40 over 3, this is minus 80 over 3. All right, we're almost there. Now we have to put this over the common denominator. So this is equal to 2 pi times 240 over 3 minus 80 over 3, which is equal to 2 pi times 160 over 3. And if I multiply 2 times that, that gives it 320. So this would be 320 over 3 times pi. And that would be the volume of that particular shape. But the overall structure, again, the important thing over here is simply to figure out what's the best way to slice this up. And if you were to go horizontal like this and try to build a washer and try to find the dV of the washer, the problem is that the inner and outer radius belong to the same equation or relative to the same equation. That doesn't work. You want the upper and lower bound of your volume to be bounded by the two separate equations. In this case, it's bounded by y equals 4 at the top, and it's bounded by y equals x squared in the bottom. That's a better way to go. So you go ahead and get a hollow cylinder as a dV, and that will allow you to find the volume of the structure. That's how you do that. Now we're going to do something slightly more challenging. The concept is the same. We have an area defined by 3 equations. The equation x squared plus y squared equals 1, which would be a circle. We're only going to take a quarter of that circle because the other 2 equations are the x-axis and the y-axis, which then define the area right here, which we're going to rotate. So this is our x-axis right here. This is our y-axis. Now when we take this area right here and we rotate it about the line x equals 2, we end up something like this. It's kind of like a section of a donut, but of course a donut would have a complete circle and would go all the way around like this. But what we're doing here is we're only going to go halfway, 180 degrees, so a half rotation. and we're only going to take a quarter of the shape of the donut, and we're trying to find the volume of that. How do we do that? Well, again, it all comes down to find the correct dV, the correct slice that we can start integrating upon. So if we slice it like this, how about if we do this here? We're going to slice it in this direction. That would be a good way to slice it, because you can see that the inner radius, the radius from the slice, because it would be like a half a washer, the inner radius would be from there to the line x squared plus y squared equals 1, and the outer radius would be to the line y equals 0, the y-axis, or I should say x equals 0, the y-axis. So let me draw the washer. So here's my washer, and it's going to be a half. There we go. So there's my half washer. And notice that the inner radius from there to there, this would be R1, and my outer radius from there to there would be R2. And so here you have my inner radius, this would be R1, and my outer radius, that would be R2. Okay, what is the volume of that half washer? The volume, dV, would be equal to the area of the washer. That would be the area times the thickness. Now the thickness here would be in the y direction. That would be small little dy. So it's the surface area times dy. And the surface area is defined by the area of the whole disk minus the area of the hole. So it would be equal to pi times r2 squared minus pi times r1 squared. Now since we're only doing half of it, we of course have to also multiply it times 1/2, like so. And so that would be the whole disk minus the hole times the thickness dy. And then we're going to substitute into R1 and R2 what R1 and R2 are equal to in terms of x and y's. Now R1, actually R2 is the easiest one. R2 will go from this point to that point, which is exactly 2. So that's easy. And R1 would be equal to the full distance 2 minus this distance, which would be the x distance from there to the equation x squared plus y squared equals 1. So we can factor out a pi. So we can say that dV is equal to pi over 2 times, remember R2 was the full distance, which is 2, so it would be 2 squared, minus R1 would be 2 minus x. So 2 minus x quantity squared times dy. All right, we're almost there, because now we have an x and a dy. We of course want the same variable there, so instead of x we want to write something in terms of y. So we go back to this equation right here. We can say that x squared plus y squared equals 1, so therefore x squared equals 1 minus y squared, or x equals the square root of 1 minus y squared. So instead of writing x, we can write 1 minus y squared. So this can be written, dV can be written as pi over 2 times 4 minus the quantity, 2 minus, and that will become the square root of 1 minus y squared quantity squared. We'll have this and a dy. All right, let's simplify that now and see what we end up with. So dV is equal to pi over 2 times 4 minus, we're going to square this, so it would be 2 squared is 4, but the minus would be minus 4. And then the product of those two would be minus 2 times the square root of 1 minus y squared. Of course, with this minus, that makes that a plus. And finally, this quantity squared, that would be plus 1 minus y squared, the square root of that squared, so the square root disappears, but the plus will then be exchanged with a minus because of that, times dy. So I actually did 2 steps all at once, which is a dangerous thing to do. I squared this and I applied the minus sign all at once. So this gives me 4 with a minus, minus 4. The product of those 2 times 2, that would be 2 times a minus, the square root of 1 minus y squared, times 2 would be 4 times that. Ooh, I'm glad I checked, because I think I just made a mistake. This should be 4 times, because it's twice the product of those two, so twice the product of the two would be 4 times that. I get a negative times a negative, which gives me a plus. And then finally, this quantity squared with the minus, that would make it a square, would make it a plus, but with this minus makes it a minus again. And I have to be careful. I need to put some parentheses around that. Oh, that's what I get from skipping steps. Bad thing. Because when I square this, I get 1 minus y squared. That would be a positive, but then with the minus in front of it, that makes that a minus again. The minus has to apply to both, like that. All right, I have one more negative to get rid of. And so I can combine these. The 4 minus 4 is 0. So now I end up with dv is equal to pi over 2 times, let's see here. This minus times this minus, that makes that a plus. That makes that a minus. So I can write this as y squared minus 1 plus 4 times the square root of 1 minus y squared quantity dy. All right, are we ready to integrate? Well, kind of and kind of not. If I now want to find the total volume, I simply have to integrate the dv. So my concept here is that the total volume of this structure will be equal to the integral of all the dv's. So I'm going to go ahead and put in a bunch of washers, add them all up. That gives me the total volume, which of course is the definition of integration. Notice that this will be easy to integrate, but what about that? 1 minus y squared, take the square root of that. I don't have a proper dy. I have a little problem there that I need to remedy. So I'm going to do this one step at a time. So here, this is equal to the integral of, and I can take the pi over 2 outside the integral, of the quantity y squared minus 1 times dy. And then I know how to integrate. And then I have plus, I can take the 4 outside the integral sign. That would be 2 pi times the integral of the quantity 1 minus, I got a little ahead of myself, 1 minus y squared to the 1/2 power dy. So what I did was I took the 4, brought out here, made it 4 pi over 2. 4 divided by 2 is 2, so that's 2 pi. And so I'm going to integrate 1 minus y squared to 1/2 power dy separately from this, because this is easy to integrate and that is not. Okay? I'm not going to go ahead and integrate the first part. Now, what are my limits of integration? I'm going to integrate from y equal 0 to y equals 1, because the radius is equal to 1, so that would be from 0 to 1, 0 to 1. So let me integrate this, and I'll get back to this later. All right. So v is going to be equal to, we get pi over 2 times y cubed over 3 minus y, evaluate from 0 to 1. Now notice when I plug in the lower limits, I get 0, so I don't have to worry about the lower limit, only the upper limit. And of course that would be plus, and I'll leave that alone, we'll get there later. So v is equal to pi over 2 times, that would be 1 over 3 minus 1, and so that would be minus 2/3, so v equals pi over 2 times minus 2/3, and the 2's would cancel out, so that would be equal to, v is equal to minus pi over 3. Let me get out of your way so you can see what I just did. So I simply simplify that and end up with a negative portion. Of course, you know the volume is not going to be negative. This portion, of course, will be much bigger than minus pi over 3, which you'll get a total positive value for the volume. But the question is, what is the second part of the integral? We'll get to that in just a moment. So far, this part is done. We got a minus pi over 3. Now, what about that part? How do we integrate that? Well, the best thing to do there is to do some sort of substitution. So what we're going to do here is substitute sine of theta for y and see if that works. So let y equal the sine of theta, which means that the square root of 1 minus y squared, so therefore the square root of 1 minus y squared will become the square root of 1 minus the sine square of theta. And that should ring a bell, because 1 minus sine square theta is equal to the cosine square theta. So that's equal to the square root of the cosine square of theta, which is equal to the cosine of theta. All right, that looks a whole lot better to integrate than 1 minus the square root of 1 minus y squared. But now we need a d theta. We have a dy there, so how do we relate that? Well, if y is equal to sine of theta, then we should be able to figure out what a d theta is from that. So from here we can say that dy d theta is equal to, the derivative of sine is the cosine of theta. So therefore dy can be written as, from here we can say that dy is equal to the cosine of theta d theta. So if we're now going to write this times this, we end up with cosine, because cosine is the replacement for this, and instead of dy we have to write cosine of theta d theta. So now we can say that the square root of 1 minus y squared times dy can be written as the cosine square of theta d theta. So now I have another problem. I don't know how to integrate the cosine square of theta, so now I have to have another substitution. Or at least not a substitution as much as maybe a nice, what we call an identity, a trig identity to get rid of that. And so we say, oh, I know what that is. That is equal to 1/2 times 1 plus the cosine of 2 theta, and I still have the d theta there. Now that's much better because I'm able to integrate this. That's not a bad integral to integrate. Don't forget you still have the 4 and you still have the pi over 2, so that gives me 2 pi times 1/2. So now let's go back over here. So instead of writing 2 pi times this, I'm going to write plus, and let me use a different color so you can see how that's related. Okay, so instead of writing this times this, which is what I have over here, I'm going to write this instead. So that is equal to 2 pi times the integral from 0 to 1 of 1/2 times the quantity 1 plus the cosine of 2 theta d theta. I think I got that right. All right. Now notice the 1/2 times 2 pi, that cancels out, and I'm simply left with a pi. So there we get pi, and I'm going to break this up into two integrals. Pi times the integral of d theta plus pi times the integral of the cosine of 2 theta, and I need a 2d theta here. So I'm going to write a 2d theta. Since I multiply this times 2, I have to divide by 2. All right. Now what are the limits? The limits have to be theta limits, and we'll get there in just a moment. So I had these, of course, were y limits. So y equals, from y equals 0 to y equals 1. We have to convert that to theta limits, and we'll do that in just a moment. So this here will be equal to pi times theta. And now I have to have the theta limits. And if I integrate this, I end up with the integral of cosine of 2 theta as the sine of 2 theta. So we get plus pi over 2 times the sine of 2 theta. And again, I need my theta limits. So how do we figure out the theta limits? Whoa. All right. Next step. I need to find my limits. And so I can say, how do I go back to my relationship here? Where do I go? Okay, let's go back over here. Since y is equal to the sine of theta, y equals the sine of theta, I can then say that theta is equal to the arc sine of y. So whatever number I plug in for y, I would get the corresponding theta. So that might help. So if y is equal to 0, so theta, when y is equal to 0, is equal to the arc sine of 0. Well, what should be the angle to get 0 for sine? Well, that is 0. So therefore, when y is equal to 0, theta is equal to 0. Okay, that's my first limit. So my limit for theta would be from 0 to the upper limit. So now to get the upper limit, I plug in theta when y is equal to 1 is equal to the arc sine of 1. So what angle do I get when the sine is 1? That would be 90 degrees or pi over 2. So therefore I have theta equals pi over 2, which is the upper limit. And so we put the upper limit over there, pi over 2. So 0 to pi over 2, 0 to pi over 2. All right. So here when I integrate that, and then I apply the limits, when I plug in the lower limit I get 0, plug in the upper limit I get pi over 2. So pi times pi over 2 would be pi squared over 4. And over here, when I plug in the upper limit, what do I get? Well, when I plug in the upper limit for this, 2 times pi over 2 is pi. And the sine of pi is 0. And when I plug in the lower limit, the sine of 0 is also 0. So this simply drops out and doesn't contribute. So this is the only contributing factor. So what I have left is minus pi over 3 plus pi squared over 4. And make sure I have all the constants in here. So I end up with 2 pi over here. The 2's cancel out. And I ended up with a half. That would be pi over 2. And when I plug in the upper limit, I get pi over 2. And let's see here. Am I missing something? I thought I was missing something. Oh, that's this pi over 2 here. Pi. Oh, I'm good. It's good. This is okay. And so this is equal to pi squared over 4 minus pi over 3. And so this is equal to pi times pi over 4 minus 1 over 3. Well, it doesn't matter how we write it. This is basically the correct answer for the volume. And that's how we do that. And then here's our next example of how to find the volume of something that we rotate. Here we're taking the circle equation again, x squared plus y squared equals 1. So we have a nice circle here. All right. Then we have another equation, y equals 1/2, right here, the line. And so you can see that the circle is being cut here by this line. And we want to take this area right here and rotate this area about the y-axis. What that does is it creates kind of like a dome shape. I try to draw it right here. So here's the top of the sphere now, because what you get now is a sphere. When you take the whole thing and rotate it around, if you take this whole circle, rotate around, you get a sphere. It's basically cutting off the top of the sphere, and there it is, and we're trying to find the volume of that. How do we do that? Again, we try to find the correct dV, a correct small volume section right here. And so let's do that. Let's slice it like this. Let's take a slice like that. And this would therefore be our dV. And so let's draw the dV out to the side so we can take a look at it. It's always a good idea to take your dV and set it to the side and take a close look at it. When you do that, your dV would look like this. It would look like a disk. There's a small little thickness like that. And so the radius of the disk, of course, would be r. And the thickness of the disk would be dy, right? Because it would be a small little thickness in the y direction. So we call that a small little dy. And so the r, the radius, would be this distance right there from the y-axis out to the edge of that disk. Okay, now we want to define the volume of that. So that would be a small little volume segment dV, and the volume would therefore be equal to pi r squared, which would be the area of this disk, times the thickness dy. And of course, r and y are not the same variables, so now we have to convert r into x and y variables. So notice that this distance right here is from the y-axis to the edge of that disk, so that would be defined as x. So we can write this now as pi x squared dy. But we still cannot integrate x's and y's in the same integral, so now we have to convert from the x squared in terms of y. So we look up here, we can say, all right, x squared therefore is equal to 1 minus y squared. So instead of writing x squared, we can write 1 minus y squared. So our small little volume segment is equal to pi times 1 minus y squared dy. And now I'm ready to integrate that. Now I can find the total volume, because what I'm going to do is I'm going to slice this all up, add up all the slices, summing up all the slices like taking the integral. So therefore v is equal to the integral of all the little dv's, which is equal to the integral of all d. And I can take the pi outside integral sign. So pi times 1 minus y squared dy. And the limits of integration, I'm going to integrate from here to there. So that would be from 0.5 all the way up to y equals 1. So from y equals 1/2 to y equals 1 are the proper limits in this case. That's a fairly easy integral to integrate, so let's go ahead and do that. So this is equal to pi times integrate 1, that becomes y, minus integrate y squared, that becomes y cubed, divided by 3. And the integral limits are 1/2 to 1. So I can plug in the limits. When I plug in the upper limit, so v is equal to pi times, when I plug in the upper limit, I get 1 minus 1/3, minus when I plug in the lower limit, and of course always use parentheses so you don't make a sign error. So minus, plug in the lower limit, I get 1/2, minus when I plug in 1/2 there, I get 1/2 quantity cubed divided by 3. Okay, now we need to do a little arithmetic here. Make sure we get this right. So we have v is equal to pi times 1 minus 1/3. Minus, I'm going to leave the parentheses on for one more iteration, because here we have 1/8 divided by 3, which is 1/24. So minus 1/24. Like that. Now we can get rid of parentheses by applying the negative sign. So this is equal to pi times 1 minus 1/3 minus 1/2 plus 1/24. Okay, to add all that together, we want to find the common denominator. So v is equal to, it looks like common denominator is 24. So pi times 24/24 minus 3 goes into 24 8 times. That would be 8/24. 2 goes into 24 12 times. So that would be minus 12/24. And then plus 1/24. Okay, so minus 8 minus 12, that's minus 20. Subtract from 24 is 4, plus 1 is 5. So finally, v is equal to 5 pi over 24. And that would be the final volume of this section of that sphere. And that's how we do that. Here's the next example of how to find the volume of an area that's being bounded by some equations and rotated about an axis. So here we have the equation y equals minus 3x plus 6 right here. And we're also bounded by the y-axis and the x-axis, so that gives us this little triangle right here. And then we rotate that about the y-axis. That gives us a nice cone. And we're going to try to find the volume of this cone using this particular method. All right, the best way to do that is to slice it, and a good slice probably would be to slice it like this. We get a small little disc. All right, and so that disc will give us a small little volume dV. And we can then draw the disk right here. It's always a good idea to draw your small little volume, dV, and then determine what that volume is equal to. And in this case, we can say that the disk has a radius r, and the thickness would be a thickness dy. So therefore, your d volume is equal to pi r squared dy. Pi r squared, of course, is the area of the disk. Dy is the thickness of the disk that gives you the small volume dV. All right, so what is the value for r? R is, of course, the distance from the y-axis down to the edge right here. So that would be r. In this case, r has to be equal to x. So therefore, we can write that this is equal to pi times x squared dy. We still have one more problem. We have an x squared, and when the dy, we cannot integrate x's and y's together like that. So now we have to express x in terms of y. Here's our equation. So when we take this equation right here, we can say that y equals minus 3x plus 6. We put the 3x over here. That becomes a positive 3x is equal to 6 minus y. And therefore, x is equal to 6 minus y divided by 3. Or x is equal to 2 minus 1/3 y. So instead of writing x squared, I can write 2 minus 1/3 y and place it in there. So therefore, my dV now becomes pi times the quantity, 2 minus y over 3, quantity squared dy. And I'll go ahead and multiply everything out. We have a binomial there. We'll square the binomial. And so we now say that dV is equal to pi times, that would be 4. Twice the product of those two, that would be minus 2/3 y, and that would be minus 4/3 y. And squaring the last term, that would be plus y squared over 9 times dy. And so now I have my volume, my disk, that dV, expressed in terms of y only, and I'm able to integrate that. So therefore, I can say that the volume is equal to the integral of all the dV's. So what we're going to do is slice this up in an infinite number of slices, add them all up, which of course is the definition of integration. And so that means that this is equal to, we take the pi outside integral sign, pi times the integral of 4 minus 4/3 y plus y squared over 9. The whole thing multiplied times dy. And now I need my limits of integration. I'm going to integrate all the way from the bottom to the top of the cone, all the way from 0 to 6. So our limits are y equals 0 to y equals 6. Now go ahead and do that integral. That's a fairly easy integral to do. So volume is equal to pi times 4y minus 4/3 y squared over 2. Add 1 to the exponent, divide by the new exponent, plus y cubed over 3 times 9. And so the integrals are, the limits are from 0 to 6. Okay, I think I want to simplify that just a little bit more. So this 2 comes out with that 4. And so let's write this as pi times 4y minus 2/3 y squared and plus y cubed over 27 from 0 to 6. All right. I always like to have it as clean as possible so you don't make mistakes. When we plug in the lower limit, we get nothing but 0, so we can ignore the lower limit. We only need to worry about the upper limit. So v is equal to pi times the upper limit. So that would be 4 times 6, which is 24, minus 2/3 times 6 squared, which is 36, and plus 6 cubed, that's 6 times 6 is 36, times 6 is 216, divided by 27. All right, simplifying that, 3 goes into 36 12 times, and 27 goes into 216 8 times, that's 160, that's 56, yep, exactly 8 times. So this is equal to pi times 24 minus 24 and plus 8. Of course, 24 minus 24 cancels out. And finally, we get the result of 8 pi as being the volume. All right, now in this case, we can actually check to see if we did this correctly. Here's a cone, and we should know from geometry that the volume of a cone is equal to 1/3 the area of the base times the height. All right, so let's do that. So that would be equal to 1/3. The base is, of course, right here. We have a disk the size with the radius 2, so it would be pi times 2 squared, that's the area of the base, and the height is 6. And so this is equal to 4 times 6, which is 24, divided by 3 times pi, which is 8 pi. And sure enough, we get the same answers we did over there. So looks like we did everything correctly. And that's how we do that using calculus. And here we're doing another example of how to find the volume of something, but here instead of rotating an area around an axis, we're simply going to find the volume of a square base pyramid. The base of the pyramid is 8 by 8, the height is 6, and the center of the base is located at where the x and the y-axis cross. So how do we find the volume of something like this? Well, the best way to do it is to find a small little dv, a slice of that pyramid, and what we can do is simply slice it like this. There we go, there's my little slice, and give it a little bit of thickness to it, like so, and that's then my dv. And let's say that dv can be expressed, let's say here, if the sides of this little volume element is a, so we get a by a times the thickness, which would be dy. So we can say that the dv is equal to the area of this slice times dy, and the area is equal to a squared dy. The question is, what is a equal to? Well, the way to do that is imagine again that the y-axis goes right down the middle of the pyramid. So the distance from that point where it goes right through that volume element to the side of the pyramid, let's call that x. That is the distance from there to x in the x direction. The question is, what is that x equal to related to y? To find that, let's draw a line from the very top through this very edge down to the side of the pyramid where it touches this thing right here. So we can go right down like this. And this line is a straight line, a y equals mx plus b type of line. Y equals to mx plus b. And all we have to do is find the slope of that line and find the intercept. The intercept is easy. That is right there where it crosses the y-axis. So we know that y is equal to mx plus 6. What about the slope? Well, the slope will be the rise over the run. In this case, the rise is a -6 because we drop, and the run is half the base of the pyramids. From the center to the edge would be 4. So that would be y is equal to -6 over 4x plus 6, or y equals -3 over 2x plus 6. So that's the equation describing the edge of the pyramid at the middle, not at the corners, but at the middle of the pyramid, which defines the size of that little dv element right here. We know that the distance from there to there would be equal to x, and we can then relate x to y in terms of this equation right here. So now we're ready to express what the area is of that. Notice that a is twice x, so instead of a we have to write 2 times x. So this is equal to 2x quantity squared times dy. Notice a is the full side of that element, x is only half of it, so we need 2 x's to make up the 1a. Okay, now we're ready to continue. Now we want to express this in terms of y because we have a dy there. And here's the key, there's a relationship between x and y. So let's solve this for x and then replace that in for x over there. So let's first multiply both sides by 2. We get 2y is equal to -3x plus 12. That way we get rid of the divide by 2. Now we want to move the 3x to one side. 3x equals 12 and move the 2y to the other side. And now divide both sides by 3. We get x is equal to 4 minus 2/3 y. Okay, now we can take that and substitute that back in for x over there. And when we do that, we get the following. This is equal to the quantity 2 times x would be 4 minus 2/3 y, and the whole quantity squared times dy. First, let's get rid of parentheses. So this is equal to 8 minus 4/3 y quantity squared dy. And then if we go ahead and square all that, we get this is equal to 64 minus twice the product. Now 8 times 4 is 32, times 2 is 64, so minus 64 over 3y, and then plus square that, we get 16 over 9 y squared, and the whole thing times dy. And now we have a nice volume element expressed in y variable only. Now we can go ahead and integrate, because the volume is equal to the integral of all the dv's. So what we're going to do is slice up all the whole pyramid, all these slices, add them all up, and of course that's the definition of integration. And so this is going to be equal to the integral of 64 minus 64 over 3 times y plus 16 over 9 y squared times dy. And the limits of integration, we start from the bottom of the pyramid where y equals 0 to the top of the pyramid where y is equal to 6. So we get y equals 0 to y equals 6. Now all we have to do is integrate this. So v is equal to, this becomes 64y minus 64 over 3 y squared over 2. Add 1 to the exponent, divide by the new exponent, plus 16 over 9 times y cubed over 3, evaluated from 0 to 6. Now notice when we plug in the lower limit, we get nothing but 0, so we can drop the lower limit. We just need to substitute in the upper limit. Well, first of all, we can go ahead and say 30, that's 32 over 1, and well, let me rewrite it so it's a little cleaner. So this is equal to 64y minus 32 over 3 times y squared, plus 16 over 27 y cubed, all evaluated from 0 to 6. All right, it's a little cleaner. So let's plug in the limits. V equals, we plug in 6 here, 6 times 64, that's 360, that's 384, minus, plug in 6 here, that's 36, 36 divided by 3 is 12, 12 times 32 is, same thing, 384. All right, plus, there we have 16 divided by 27 times 6 cubed. Now 6 cubed is 216 divided by 27. 27 goes exactly into 216 8 times. So here we get 384 minus 384 is equal to 16 times 8, which is equal to 128. And that would be the volume of that pyramid. Now, just to check to make sure we did this correctly, let's check it with our equation where we know that the volume of a pyramid is equal to 1/3 the base times the height. Okay, that's equal to 1/3 the base. The base would be 8 by 8, so 8 times 8. And the height would be 6. 6 divided by 3 is 2. 8 times 8 is 64, times 2 is, yes indeed, 128. That gives us the same answer, so we know we did it correctly this time. All right, so that's how we find the volume of a pyramid. Again, the technique is the same. We find the little slice. We are able to define the slice in terms of area times the thickness. Then we change our variable to something that's more practical, x and y. Since we have a dy, we then have to convert the x into a y variable, and then we integrate. And that's the technique we use on all these types of problems. So hopefully, these last 10 examples have given you a really good idea of how to do that. In the future, I will also make some videos in which we actually do 3-dimensional integration over a volume in all 3 dimensions, x, y, and z, and sometimes we'll also use polar and even spherical coordinates. So that will come later, but at least now you have a good handle on how to find the volume using these kind of techniques.